that I am Vishruth. I would basically tell you a little bit about myself first. So I am a master, like I just completed my master's study from TU Delft in vehicle engineering. And currently I'm pursuing a PhD in the similar field. So again, for autonomous vehicles. And this slide or this presentation would be on vehicle platooning for autonomous vehicles, which was the topic for my master's thesis. So without further ado, let me start with the overview of what is going to happen in this presentation. Firstly, I would give you an introduction of what vehicle platooning is, what kind of sensors do we require to make it happen, what are the different kind of systems that we use in it, like CC, ACC, and CACC. What model is it used? What model is used to make the vehicle platooning happen? So longitudinal model in our case. Then the architecture for adaptive cruise control and the cooperative adaptive cruise control, after which would be the evolution of how the vehicle platooning algorithm is changing and what can it be used for. And finally, the future scope for what can it be used for in later stages. So an introduction. What exactly is a vehicle platoon? So if multiple vehicles are grouped in one at the back of each other in such a manner that only the front vehicle has to lead the way manually and all the other vehicles can drive automatically behind it, it's called a vehicle platoon. Some of the advantages of vehicle platoon are these. So because the vehicles are going quite close to each other, there is a reduction in aerodynamic drag. So what happens with this is the fuel consumption reduces, hence it's good for the environment. Also, the vehicle throughput increases. So vehicle throughput is nothing but in a small amount of area, how many cars can fit. So in manual driving, there are less cars in a particular area than in vehicle platoon or automated driving. Now, apart from that, as we know, if computers are way faster, they have way faster reaction time when compared to the humans. So in that case, there is a huge chance that the traffic would reduce as well. So some of the key terms that I would like you guys to know before I start with the presentation are these. So first one is the headway. Headway is nothing but measurement or distance or time in between the vehicles. So if you look at the left, you're showed distance headway. So there are two settings where first is when C1 is at a velocity of V1 and the second is when C1 is at a velocity of V2. We can see that the velocity V2 is greater than V1, but the distance between the cars is the same. But if we look at the time headway, this basically tells how much time should the other vehicle be ahead of you. So now V2 has a greater distance. Like if you look at the distance in between C1 and C2, when the car 1 is moving at a faster speed, they have a greater distance in between them, which makes sense because if you're moving faster, there should be a greater distance for safety reasons. Now let's talk about string stability. So string stability is one of the things that is specific to vehicle platooning. It is described as the amplification in the upstream direction of either distance error, velocity, or acceleration. Think about this. There's a platoon of 5 vehicles and there was a gap created between, or an error induced in between first and second vehicle. So as we move on in the time, through the stream, which means from vehicle 1 to 2 or from vehicle 2 to 3, this error should not increase. This should only attenuate. There's a small video that I would show to make it a bit clear. So at first, all the cars are equidistant, but because it's manual driving, there's some error being created in between them. And when that happens, the coherence is lost. So this shows us that this was string unstable. Let's talk about the sensors that are required to implement vehicle platooning or vehicle following. So the main criteria for this is distance sensing. So how far ahead is the other vehicle from your vehicle? This can be done using various sensors like LiDAR, radar, or ultrasound sensors. But one of the most used or the most common sensor that we use for this is radar. Now, this is basically for adaptive cruise control. For cooperative adaptive cruise control, you also need communication between the vehicles. So for that, Wi-Fi works. Now, let's talk about the terms that we would be using. So one is CC, which is cruise control. So CC is nothing but how your vehicle, like it's just controlling the speed of the vehicle to go at a constant speed or velocity. So cruise control just lets you cruise at a constant velocity. Adaptive cruise control, on the other hand, it maintains a safe distance between the vehicles. This distance is predefined when the adaptive cruise control system is designed. If we move from adaptive cruise control to cooperative adaptive cruise control, it's nothing, the difference is not very big. It's just adaptive cruise control with communication, but the results that we get are quite drastically better. So why should we choose cooperative adaptive cruise control over adaptive cruise control? So communication allows more information to be shared. So what is the position of the vehicle, which velocity is it going at, and what control action is it going to take? So all these information can be used in a productive way to decide on other vehicles' control action. Also, if you use cooperative adaptive cruise control, the distance or the safety distance between the vehicles can be reduced, which would increase the vehicle throughput by a bit further. As the information is being shared with other vehicles, it has a faster response time as well. And finally, the properties that we talked about, string stability, CACC has string stability, whereas in ACC, it is hard to get string stability. What kind of model are we going to use? So basically, the vehicle platooning algorithm that I'm going to talk about is the longitudinal model. It has control over the acceleration pedal. So you can control either the acceleration or velocity of your model. And because it's only the acceleration that we are controlling, it's a one-dimensional model, which is the longitudinal model. Now, the description of model goes like this. The basic need of a control system is to attenuate the error or push the error to zero. So in a control system, what you do is you have a desired value and the actual value. So you get the discrepancy between these two values, and the aim of your control system is to make this difference zero. So basically push your actual value to the desired value. In this case, because we need to have a safety distance between two vehicles, we define the error as desired distance that is subtracted by the actual distance. In an adaptive cruise control model, generally PID is used just to reduce this error to zero. And experimentally, it's only PD. It has been established in various companies and papers that a PD use is enough for adaptive cruise control. Talking about the cooperative adaptive cruise control model. Now, the desired distance between the two vehicles is R plus HV. So V is nothing but the velocity of the vehicle. H is what we talked about, the time headway. So that time multiplied by the velocity gives us one particular distance that the car has to be ahead of. And R is a safety standstill distance. So even if your vehicle is at rest, there should be a safe distance between those two vehicles. So that is R. We define the error as this. So error is nothing but the difference between two vehicles, the positions of two vehicles. Now, you have to note that the positions are from rear bumper to rear bumper. So QI-1 is the position of the vehicle QI-1, of the vehicle I-1. QI is the position of vehicle I. Li is the length of vehicle I. And R plus HVI is the distance, the desired distance. So we define the error as that. The basic model that we would be using is this. So this is nothing but a longitudinal model which covers distance, velocity, and acceleration. Interesting fact, not interesting, but just a fact that these three terms are just derivatives of each other. Now, you look at this final equation in there. This is just a delayed response. So when you press the acceleration pedal, it's not, the acceleration doesn't go up to a level instantly. There is a delay. So in here, the delayed response is governed by this equation. Now, the error dynamics, if we talk about, as I define the error here, the error dynamics are nothing but the derivatives of those errors, which we would need to stabilize in order to get their control action. So these are a few, like a set of equations, which I would go through in a quick way. So error, the derivative of error, where Q becomes velocity, QI becomes velocity, and V becomes acceleration. Again, you differentiate that. we see the term AI dot here. And through the last equation, we can see that the delayed response has to be put in there. We get the double derivative of error, and we substitute the other value as well. Now, we get the triple derivative of error, which we use to stabilize the error. So now we have a virtual input that we need to get in order to stabilize the whole equation. Finally, if we put the virtual input in a manner that our equation gets of the form E dot equals to minus C1 E minus C2 other integral parts of E, which is for E triple dot, it would be E double dot, E and E dot. So if we attain this particular form of our equation, then the error would get stabilized. So if we choose that, the governing equation for our control action is this at the bottom of the page. So finally, if we put all those things together that we just derived, we get these two models. So this is nothing but the error derivative model. And this is the basic model that I talked about initially, which covers distance, velocity, and acceleration. Now, also the input is involved in this equation. So it's just an augmented system space, state space. If we use this control input, here is one of the simulations that we get. The red vehicle is the leader vehicle, and all the other vehicles, they'd never lose coherence with it. As you can see, when the speed increases, the distance between those vehicles increases as well. That is because of the time headway. And finally, when the car stops, they have a standstill distance in between each other. So the control system works and CACC works. Some of the other uses for adaptive cruise control and cooperative adaptive cruise control would follow, like vehicle following. So if you don't have a platoon, just two vehicles, then also you can use adaptive cruise control or cooperative adaptive cruise control. Vehicle platooning, as I described in the whole of the presentation. Merging maneuvers. So if there are different vehicles in different lanes and they all have to merge in one lane, we can use these algorithms to do that. Splitting maneuvers. So when you have one platoon and you want to split into multiple platoons, the same set of equations can be used. And overtaking. So overtaking is something which I would describe a little bit later. Now, what is the approach that we get when we do the merging or splitting maneuvers? So here is the approach for merging. So at first, vehicle 2 would align to vehicle 3. So these are vehicles in two different lanes, and vehicle 2 would just align to the vehicle 3, after which a gap would be created in between vehicle 1 and vehicle 3, and finally vehicle 2 would merge in between vehicle 1 and 3. So the spacing policy would be in the first stage, in between 2 and 3, the desired distance is 0, after which we increase the distance and we reach the headway. So the distance between 2 and 3 should be the headway or the desired distance between them, and so should be between vehicle 1 and vehicle 2. And finally, we attain the configuration where vehicle 1 and vehicle 2 have a safety distance R plus HV, and vehicle 2 and vehicle 3 also have that particular safety distance. This is one of the simulations for the merging maneuver. The red vehicle is a virtual vehicle. You don't need to look at that, but this is the aligning phase. So these two vehicles align with each other and these two align with each other. Finally, merging, the gap is being created, and in the meantime, the cars are merging in the same lane. So this was a merging maneuver. If we talk about splitting, it's similar. First, again, the red vehicle is a virtual vehicle. You don't need to look at that. So the gap is being reduced, and finally, there comes a point where the vehicle starts leaving. And the final stage for splitting maneuver is when the vehicles are aligned with the other vehicles. So vehicle 5 with vehicle 4 and vehicle 3 with vehicle 2. Now, let's talk about overtaking. So overtaking is nothing but a combination of splitting and merging maneuver. If you look at the left side, the first figure, it's C1, C2, and C3. So these three cars are in a platoon or in a lane. What it does is C1 leaves the lane, then it does the splitting maneuver and it aligns with C2. And then the merging maneuver takes place. So C2 and C1 are aligned with each other. There's a gap creation between C2 and C3, and finally C1 merges in. So as you can see in the initial configuration, there was C1, C2, and C3. Finally, it is C2, C1, and C3. So overtaking has been established, or it's done successfully. Now let's talk about some recent developments that has taken place in the field of vehicle platooning or vehicle following, CACC. So I'm going to start with talking about a problem case. So in this case, let's consider there's a platoon of these 4 vehicles, and all of them are the same car, and the acceleration or velocity has saturated. So they're working at their maximum potential limits. Because of some reason, a faulty measurement or a slippage on the road, there is a small distance created or a small error created between vehicle 1 and vehicle 2. So what would be the plan of action? And because there is a small distance created between V1 and V2, the distance reduces between V2 and V3. So the first thing would be the vehicle V3 would be asked to apply brakes, which it does. Vehicle 2 should accelerate, but as we talked about, it's running at its full potential, so it cannot accelerate. And finally, the distance between V2 and V3 can be reduced, the error can be reduced to 0, but V1 and V2 have a stagnant error in between. To show this in simulation results, these are the results. So you can see the vehicle 3 has a constant gap in between, which means it cannot reduce the gap. So this is the current algorithm that we use. So what I propose to do is to use a bidirectional communication. So in the previous CACC algorithm that I derived in this presentation, we had only the error which is from the front vehicle to the back. But now, if we look at both the error in front and error from the back vehicle, we can decide that we need to brake for the vehicle at back or accelerate for the vehicle in front. So it is nothing, the error in front as talked about earlier is the same. The error at the back is also the same, but with a negative sign. Why is there a negative sign? So let's consider these 3 vehicles. If the distance between V1 and V2 decreases, V2 needs to brake to create that amount of gap again. But if the distance between V2 and V3 is reduced, V2 needs to accelerate. And hence, this negative sign signifies the opposite control action that the car needs to take. So the total error is defined as this, which is nothing but some weighting factor for error in front and some weighting factor for error in back. So this sum of C1 plus C2 should be 1. So error dynamics are just the derivative of error. Now let's talk about the same case again. There is an error created in between V1 and V2, which creates some error in between V2 and V3 as well. V3 is asked to apply brakes, which it does. V2 is asked to accelerate, but as we talked about earlier, it cannot because it's already running at its maximum potential. After this, because the V1 can also look at the error behind, it applies brake, because of which a new error is created between V0 and V1. But as we talked about earlier, that the vehicles can look at the back as well now. So even V0 reduces its velocity, and hence the coherence is retained again. This can be shown even in the simulation results. As you can see here, there was an error created in there, but it attenuates to 0 in a very short amount of time. So this was basically the talk of my presentation. Now, I would like to throw some light on the things that can happen or that this particular topic can go in. So one is connected driving. If the information is being shared with other vehicles, you can always have a better approximation or estimation of where the other vehicles would be. And because of that, you can take actions in such a way that your driving is better or the autonomy in that particular vehicle is better. Autonomous merging and overtakes, which as described in the slides earlier, and automation in the transportation of goods. So if we are transporting a huge load of things from a factory to some retail outlet or something, so you can always have 3 trucks platooned together to take all those goods from one place to another. So if this happens, you save your fuel. You don't have to use a lot of drivers, and it goes from one place to another in a very short time. Now, difference. Because vehicle platooning, the idea behind this particular slide was formation, one behind the other. So if you use something in defense, say tanks or other things, or say even jets, you can have a particular formation which the tanks or whichever vehicles are in, so that you can keep that formation for longer. Agriculture. So all the things like sowing the seeds, watering, irrigation, it's a continuous process. You take the seeds first, you sow it in the soil, then you put the soil over the seeds, and then you irrigate. So if you have three different types of vehicles for that, or three different types of mini pods for that, you can have the platoon do the thing. So the first vehicle would go to just put the seeds in the soil. The second vehicle would put the soil over the top, and then finally irrigation. So these are some of the things that vehicle platooning can be used in.